I forgot to start recording, so we're recording now. Even though I had my little thing up there saying we're recording. All right, good. Other questions? So for presentations, right, we're going to start doing PA5 presentations on Tuesday, so a week from today. And the guidelines are as follows. So no, I don't have any office hours until next week. My last hours were this morning from 8 o'clock to 9:45. So I don't have my regular Thursday, Friday office hours this week. So for presentations to the class, the guidelines are as follows. Each group needs to present their project in order to get credit for it. The presentation can be done by one person, multiple people, everybody, it's up to you. But you should talk amongst the people in your groups if you're in a group and figure out how you want to do the presentation, particularly since we're presenting over Zoom. It takes some coordination. You can't just kind of look at each other and say, okay, you go first, So plan ahead of time how you're going to present. And basically, Tuesday morning, I'll just ask, who wants to present their project first, and we'll just kind of do it on a first come, first serve basis. If nobody volunteers, I'll just start picking out people from the participants. And I'll enable screen sharing. So when it's your turn to present, you can share your screen and just run through your code. And it's really just, showing us what your code does. I'm not looking for, any particular polish or fancy presentations or anything. Just run your script and show us the behavior of it. And what I'm trying to do is figure out, does your script do the required things? And since each person's program is going to be different from anybody else's, it's hard for me to sort of figure out how to use each person's program. And maybe there's some detail to making it work that I wouldn't know about. So if I try to grade your assignments by running it myself, unless you leave me a lot of documentation, that's not going to work well. So you're just demonstrating what your program does. And so you're required to demonstrate, and this is written in the assignment prompt, but you're required to demonstrate the 3 mandatory functions, which is showing future appointments, making an appointment, deleting an appointment. So you'll start off, you'll run your script, you'll show us the current list of future appointments, which could be empty. You'll make an appointment, show us the list of appointments that should be there. Make a second appointment, show us the list of appointments that should be there. Delete an appointment, show us a list of appointments, and that deleted appointment should be gone. And then depending on the other 3 features that you decided to implement, just demonstrate those. All right, if you have friends who are enrolled in this class who never come to class and you want to be nice to them, you might remind them that they need to present on Tuesday or possibly Thursday. As I say, we'll do first come, first serve. If people are done volunteering, I'm just going to call on people. If I call on a group to present and nobody's there, then it's a 0. So we're not going to do, some presentations Tuesday and then everybody's done. And then Thursday, somebody comes in and says, hey, I want to do my presentation now, right? So you got to be ready to do this Tuesday, 10 a.m. And we'll probably have time to get through all of these Tuesday and Thursday because that's 4 hours. And I don't think there's going to be that many groups. But, I'd like to keep it kind of streamlined if possible. So show us the behavior of your program. And then if you want to talk about, details of your code, if there's something, particularly clever that you figured out, or something that was a big challenge, you can share that with the class and so on. But you're not required to go through your code line by line and talk about it, right? We're mainly interested in what does your program do. So questions on the presentation part?
Yeah, actually I have one.
Yeah.
So does the entire group need to be present during the presentation, regardless if only one person is presenting?
No, only the person presenting.
All right, thank you.
If you care about your grade, you might want to be there while somebody else is presenting your work on your behalf. To say like, hey, you know, or if something goes wrong and they're like, oh, I guess it doesn't work, right? You might want to at least be watching to say like, no, you forgot to do such and such. But yeah, no requirement for that. Other questions, comments? All right. The other thing is Izad has asked me to remind people again, CSE 280, which is an intro to data science course, is being offered in winter. It's going to be in person. It's Friday, 10 to 12 on campus. And the only prerequisite for that is CSE 120. So everybody here is well qualified to take that. I posted an announcement a while back, and there's a link in there to a flyer, and the flyer talks a little more about what the course is, what the subjects are, and so on and so forth. I think it's being done in Python mainly. And there's also an email address in there for Ying to write and get more information. So if you have room in your schedule for winter and you're looking for, I think it's a 2-credit course, and or you're interested in learning more about data science, big data, check it out, take a look at the flyer, send an email maybe and ask for more details. And that's an option to take in winter. And then in spring, there's a CS280, which is Scott's machine learning class. And same idea, it's a 2-credit course with minimal prerequisites. So those are options, and I think our plan is to offer these 280 courses more and more to sort of give people opportunities to learn a little more about subjects that are outside the usual curriculum. And you know, data science is a course you can take more classes in that area at a university, and so on. So if you want an intro to it, that's a good option.
Can I ask a question?
Absolutely.
Can you talk about how to delete our appointment one more time?
Sure.
Thank you.
Yeah. So the first thing is there's no delete command per se in Bash that we can use to say, hey, delete these lines from a file, right? We could try to use a stream editor and write a program for sed that would, you know, go through a file and pick out certain lines to remove and so on. But that's beyond what we've been doing, right? And that's needlessly complex. The goal with this assignment is to get some practice writing more complex Bash scripts. And remember, Bash is a programming language. So we have the ability to make loops, to do conditionals, to save values and variables, to set flags and respond to them, all the things we do when we write programs. So we can use some things to help us with this. So for example, here's something that we've been talking about is this loop structure called while read variable do, and then done less than name of the file. And so the idea is everything between do and done is repeated for each line of the file. In this case, the appointments file. All right, so this structure, I'm going to put a bunch of stuff inside here. And what this will do is it will open up this file called appointments. It will read the first line, everything up through the first new line character, and it will store the contents of that line in this variable. This can be any variable I want. And then I can do whatever I want to that in here. And when I get to the done, it will go back and it'll read the second line from this file, store it in var, do whatever I want, and so on. So it's a different way to loop, but instead of looping while a variable increments from 0 to 10, it's looping while this variable takes on each line from the input file. So we can do some simple tests in here. We can just put a simple echo statement in here. And this will just show us what the value of this variable is each time that we go through this loop. All right, so I just made this file called main. If I try to run it, I'm going to get a permission denied. So I'm going to change the permission bits. I only have to do that once. So I can say main, and I can see that, you know, my loop ran a total of 6 times. And each time this variable var was set equal to this next string from the file. So we can copy this line to an output file by, instead of echoing, which you know displays on our screen this information, we can say let's echo this into you know output file. And now when I run main doesn't show me anything, but I've created this file called output file that has all of this output in it. So ask questions while I'm doing this if something's not making sense. So let's make an exact copy. Of the input. So instead of saying var equals angle bracket $var, I'm just going to echo $var. And if I run that, well, I can see, you know, I got my exact copy of my output right here. But this stuff that I wrote before is still in my file. And if I run main a bunch of times, output file just keeps getting bigger and bigger and bigger. So what's happening here is I've got my appointments file and I've got my output file. And I'm reading a line. And then I'm saying echo the line into my output file. And I'm doing that in a loop. But this greater than, this is saying append this thing I'm outputting to the bottom of this file. So if output file already has 10 lines in it, when I do this, now output file has 11 lines. So my output file is growing bigger and bigger, which is not really what I want. So what should I be doing before I do this while loop? What can I do here to, yes, good. All right, so first, let's get rid of anything that's already inside output file. And an easy way to do that is just copy dev null to output file. Remember, dev null is an empty file. If I copy that to another file, this file becomes an empty file. I could also just remove it, because if I try to append to a file that doesn't exist, it will create the file and then start appending to it. So I could also just make a remove statement here. So either way will do the same thing. So now if I say main, and then I look at output file, it's an exact copy of my appointments file. All right, so now we're going to do one more thing. Do we want to keep this line? And if we want to keep a line from our original file, we're going to say echo. We're going to echo that line into the output file. If we want to delete a line, just don't echo it. So we're not so much going through and deleting a line from the appointment file. What we're doing is reading each line of the appointment file and copying to an output. And if there's a line we want to delete, we just won't copy it. Does that make sense? Cool. All right, so let's
I got a question.
yeah.
What did you mean by not copy the line with the echo?
So let's say our appointment file has, you know, A, B, C, D, E. And we want to delete the line containing C. Well, we're going to read A, we're going to add that to our output. We're going to read B, add that to our output. We read C, and for some reason we decide we want to delete that. Don't do anything. Don't copy it to your output. Read D, copy that to your output. Read E, copy that to your output. And there you go. We've got a new file which looks like our old one, except C has been deleted. So it's not so much that we're removing it from this file. We're just not copying it from this file to our output file. It's the same thing in the end, though. We have an output file which doesn't contain that record C.
Would it be too complicated to do any of this without so many output files? Or can you use the same output file for deleting and for viewing on a certain date and for
I think the main thing to worry about is concurrent access. As long as two things don't use it at the same point in time, then it should be fine.
Yeah, so those are good points. So, you know, in the beginning of this script, we're zeroing out output files. So it doesn't matter if this was already used to view appointments or something else. But yeah, if we're not careful, if your program was being run twice at the same time, you could get into problems with this. You're totally safe assuming that that's not going to happen, though. You can just, you know, not run this program from two different windows at the same time. If you do, then you know what you're creating here might conflict with what's being created somewhere else. And then you start getting into, you know, using more clever file names, like maybe a file name appended with your process ID or something unique. But you don't have to worry about that for PA5.
okay, so it would almost be okay to just use one output file for all the time.
Yeah, I think that's probably fine. On the other hand, for debugging purposes, it may be clearer to have a separate file in each case. And you have that whole temp directory, right? You have your own directory you put under /temp/calendars. You can populate that with 5 or 6 temp files, and that's totally okay. All right, so let's throw an if statement in here. So suppose we knew that we wanted to delete this appointment from the 25th. All right, now obviously we're not going to hardwire this in our code. But so we can see more clearly what's going on here, right? If my variable is this line I just read is not equal to this, then I'm going to echo it to my output file. So here's my output file right now. So I run main, and now if I look at my output file, it's missing this appointment. Right, that's been deleted from the file basically. Why? Because I had a statement which said, hey, if my line looks like this, don't copy it to the output. If it's not equal to this, go ahead and send it to the output. So we could do something like this. Right, and in this case, delete line is a variable containing the line that I want to delete from my file. And so same thing, that will delete that. Or maybe I want to delete on a certain date. Well, how do we delete on a given date? So let's suppose our line is equal to this. Go old school. So we already went through this in the beginning of class, right? I can say awk field separator is a pipe, print field 1, and I can echo $var and pipe it into that and get the date. And I can say D equals back quote all of that. And that will give me the date of this record. So now I can say something like, find the date of the record. So echo the variable, pipe it into awk, get the first field, D is the date. And then I can say if the date is not equal to delete date. Right, so what's this going to do? We've got a delete date. This comes from somewhere, right? The user has said, I want to delete everything on this point, this date, or something like that, right? So this reads line by line from the input file, which is called appointments. We take that record that we just read, we break it up to get the first field, the stuff before the pipe, which is the date, right? This thing right here. We save that in this variable D, and now we say if the date that we pulled from that record is different from the date we're trying to delete, then go ahead and copy the record to the output. And so I've hardwired date to delete as the 16th. So here's the original appointment file. If I run main and then I look at output file, it's missing go to school on the 16th, and it's missing go home on the 16th. And all the other records are still the same. So that's just sample code. That's not PA5. That's not your delete function. That's just sample code that shows you some of the things you can do to achieve the behavior that you're after in PA5, in the delete function, in looking at future appointments, things like that. Delete all past appointments feature. Yeah, you can do that. That would be a good optional feature. Yeah, you're welcome. All right, other questions? All right, so let's switch gears here and talk about processes. And so we've started doing this a few times in a few different contexts. So we know about the command called top, right? Top shows us things that are running on our system. And on my system, I've got 341 tasks. So tasks are basically, things that are doing certain things. Total of 341 tasks on my system. 340 of them are sleeping and one of them is running. I've got 3 of them running now. I'm never going to have more than 4 of them running because I've only got 4 cores on my CPU. And you can see Zoom, for example, is using 112% of my CPU. Well, that's because I have multiple cores. So Zoom's taking more than a core. GUVC View, which is my document camera, is taking 100%. And then I've got some other stuff taking up, some smaller chunks of time. And this S column, this shows me the state of these different processes. And for the most part, this state says S, which means sleeping. So I have 341 processes on my system, but most of them are asleep. And what does it mean when we say a process is asleep? It means it's waiting for something to happen. So, you need to know when it's time to go to class. So you set an alarm clock and you go to sleep. Or you need to know when to respond in class because you've been called on. So you set something up in your brain so that when the teacher says my name, I will wake up. And I'll say, can you repeat the question? Right? So we set these little alarms for ourselves that respond to different events. Perhaps, an alarm goes off after a certain amount of time, perhaps when something happens. Perhaps, when my phone rings, I wake up and I answer my phone. So this is how most programming is done today. Now, in this course, in 121, even in 222, most of the programs we write, they start, they run, they finish. But that's really not the usual model anymore. The usual model is we start, we go to sleep, but before we go to sleep, we leave some information about when we want to be woken up. So for example, I'm going to sleep, but if the person clicks their mouse button in this part of my window, wake me up. All right, while I go to sleep, I'm not taking any resources anymore. I'm not taking any CPU time. The system is working on other things. But at some point, somebody clicks the mouse button inside a window and bingo, my code suddenly wakes up. And it's at a part of the code now that's written specifically to handle mouse clicks in that window. And it can go ahead, it can see where the click was, which button was used. It can do whatever it's supposed to do, and then it goes back to sleep. So this is sometimes called event-driven programming. And it's really the standard way we write code anymore. And so most processes are asleep most of the time. And the top command is always running because, I'm running top. So there's top right there. So there's the process called top. Its state is running. Most other things are sleeping. All right, so we've got all these processes on the system. There's an integer associated with each process called the process ID. And my process IDs, are around 500,000 right now, 500,000. But there's some processes with, small IDs. And each process is owned by someone, so it's kind of like a file. There's an owner, and this command top was running a process whose ID was 513854 that was owned by Nick. This process 2984 is owned by Root, and that's running something called Xorg. And that's part of the display manager that makes things appear on my window and, you know, makes things that I can move around and so on and so forth. So I want to look into characteristics of these processes and ways that we can interact with them from, for example, Bash. And then I want to look at these processes and see how we work with these from C, from a very low level perspective. So the command PS shows me my processes that I have running on my system. And if I create a new window, so this is a new instance of Bash, and I say PS, I get different information, right? These process IDs are different from those process IDs. I'm running the command Bash, I'm running the command PS, and so on. TTY, this is a teletypewriter. This is a holdover from the days when we had physical terminals connected to a machine, and each person using the machine was sitting at a physical terminal that had a keyboard and a printer or a display. And you could tell where that physical keyboard was attached to your computer, which port it was plugged into. Well, this is all virtualized now, right? I don't have a physical keyboard with a physical cable plugging into linux.engrcs.com or into my laptop. So there's these pseudo terminals, PTS. And so this window, my Bash session is connected with pseudo terminal 1. Here it's connected with pseudo terminal 3. This isn't really interesting to us anymore, other than the fact that this is different from that. And if I create a third window and I do a PS, now I'm at pseudo terminal 4. And again, a separate process ID, 18, 944, 841. So I can do PS-L, and that'll show me more information. So here's my command Bash. That's my shell. That's the thing that is currently running, that's printed out this prompt and is waiting for input. And its process ID is this 513.841. And PS, that's the command that I typed right here. I said PS because I wanted to see process information. And that caused a new process to be created. And that process is running the command PS. And that process has an ID of 51. But this column says, what's the ID of this process's parent? And the parent process ID is 841, which is my Bash process. So there's a hierarchy of processes. It's an inheritance structure. This is the parent process. This is a child process created by the parent. And you can tell it's a child because PS's parent process ID is the same as the process ID of the parent. Well, this Bash shell was created by something. It was created by process 513836. So I can search for that process, and it's this process right here. 513836 is a program running user bin console. Well, that's the name of a terminal program. That's what I'm running. That's giving me this box right here. If you can read up at the top, it says console, KONSOLE. That's the program that creates this window that lets me type Bash commands. And so that's the thing that created this Bash instance. And that Bash instance created these other commands that I'm executing, such as grep. And the parent of console is process ID 3384. Well, that's a small number. So that's going to be a process that was created a long time ago. And 3384 is a process called XF settings D. And so this starts to get outside our pay grade here. XFC is a windowing manager. that's used for, displaying widgets on the screen and interacting with the user. And XF settings is part of that process. And the D at the end tells us this is a server. It's called a daemon. It's a server that's hanging out and running. And if I create a new window, it's this process that's going to create the new instance of console. So both of my console windows have a parent of this this process right here. I also have an app finder. I have my mail program, and those were all created by this XF settings D. If I open a terminal window, and then I look in here, oh, that one doesn't work. Never mind. All right, but if I create a new terminal window, right, now I've got a new console process, which was just created now at 10:50, but it's still a child of 3384. And there's date and timestamp information. So XF settings D was started on November 14th. Well, that's the last time I rebooted my machine. So I can look at uptime, and my machine's been up for 7 days. So that's 7 days ago. All right, so PS-L shows me information about my current set of processes, and in particular, it's showing me the processes associated with this terminal, sudo terminal 1. So over here, when I say PS-L, I'm only seeing processes associated with whatever terminal this window is associated with, which is sudo terminal 3. But if I wanted to see processes associated with the user Nick, I can say ps-user Nick, and it will show me every process that's owned by Nick. Well, there's a lot of those because I'm on my own laptop, and so, the system boots up and most of the stuff is owned by me. And I can get more information. I can say -lu Nick and get a long display that shows me process IDs, parent process IDs, and so on. And I can do an F for full. And now I can see, the exact command that's being run, including all the switches associated with the command, and so on and so forth. So, I have a Minecraft server running on a different box, and I connect to it using this command screen, and there's the process that's sitting around, created on the 15th, that gives me access to the Minecraft server on this remote system. Here's a bunch of Zoom processes associated with this current Zoom session. Here's the thing that's making this little window up here that says recording in progress. It's a Java program. I give it an argument of 1205, and this will update a progress bar slowly so that it's filled up at 1205, which is when class ends. So this is my little visual reminder for how much time we have left in class. And that's just a Java program. And it's a process that is owned by Nick. That's me, right? I started that right before class began. All right, so there's all these processes. They're all keyed off of process ID. And it's possible to interact with these processes in a variety of ways. Now, for most of our day-to-day existence, we don't care about this stuff. We don't care about this stuff, right? We type a command, we hit enter, it's a mistake. We type a command again, we hit enter, it executes it. We go on with our life, right? We do whatever it is we want to do. And we don't really care what's the process ID, what's the parent process, and so on. But at some point, you're going to care about this. So at university, you'll get into some system programming classes, and you'll start having to deal with processes and how they interact with one another, and so on and so forth. So this is sort of kind of a preamble to some of that. But it's also, you can't really have a complete picture of an operating system unless you understand something about how processes come into existence, how they work with one another, and so on. And so let's dig deeper into this. So PS gives us our processes. If I run a command, while that command is running, I cannot interact with my bash program, right? So I'm running the command sleep, which just sleeps for 1,000 seconds. And, you know, I can type bash commands, but bash is not listening to me. This process has got to finish before I can type to bash, right? So bash is kind of off on the sidelines, and the stage is being held by this process. And we know that if I've got an infinite loop or something that's not working, or I change my mind, I can end this process by hitting Control C. So I hold down Control and print C, and I get this little symbol, and now I'm back to my shell. So now I can execute shell commands, and that works fine. All right. There's also another option, which is Control Z. So Control C says interrupt a process. Control Z says stop a process. So interrupting a process means basically kill it. The process goes away, it's done. Stopping a process is really a pause. So I'm sleeping right now. I hit Control Z, and it says this process is stopped. But if I do a PS, that sleep command still exists. The process still exists. But I have control of bash, right? Bash is listening to my commands again. So if I do a PS-L, I can see sleep is out here. Its parent ID is 206. Sorry, its parent's ID is 41, which is bash. But it's relinquished control of my keyboard, right? I can type and so on. But it's not running. It's in a state that we call stopped. And if I want to go back to running that process, I can say FG for foreground. And now I'm back to running the sleep command. So FG brings the job back into the foreground. So let me do something more interesting than sleep. Let's make a looper. We'll do this for 5 minutes. All right, so we're just going to go into a loop, and we're going to say hello. We're going to sleep 1 second. We're going to increment I, and we're going to do this until I gets up to 300. So this will loop for 5 minutes. All right, so I started running looper, and it says hello every second. All right, so if I hit Control C, it just kills it. Control X was a mistake. And I do a PS, there's no more looper running. So it's totally done. If I hit a Control Z, that stops it. And it's no longer printing anything on my screen. It's basically paused. And if I do a PS, I can see looper is still out there. That's process 841, which was process 304, which was created by 841, which is bash. And this process looper 304 created another process to execute sleep. Right? Why? Because in the middle of my script, I say sleep. Well, to run the sleep command, we have to create a new bash shell and execute this sleep command. Or do something to make this sleep happen, right? So this is a separate process. Now, if I say FG, then this comes back into the foreground and we're running the script again. And if I hit Control Z, it stops it. So let me make this a little more interesting. Let's print out the value of I. So there's looper running. If I hit Control Z, it stops it. And it's really paused, right? So if I hit FG to bring it back into the foreground, it continues from where it left off. All right, so instead of FG, I can also type BG, and that says run it in the background. So now if I say BG, looper is running again, but it's running behind the scenes, meaning I can still interact with bash. I can still say, show me my directory, show me the date, show me processes that are out there, right? But in the background, this process is still running and it's still doing its thing. And I can bring it to the foreground with the FG command. If it's in the background and I hit Control C, I'm not talking to that process, right? Control C is being picked up by bash, but looper is running in the background. So if I bring it to the foreground and I hit Control C, now I'm Control C'ing looper, and that kills the process. All right, you can also start commands in the background by putting an ampersand after the command. So if I say looper ampersand, that just starts it in the background. And I've still got access to bash, but it's running behind the scenes. So if you had a program that was going to run for a really long time and you didn't want to wait for it, you can run it with an ampersand at the end and it runs in the background. And it gives you the ability to still, do other things. And, you wouldn't do that with a program that's printing output every second, because that's pretty unusable, especially if you're in the middle of VI, because that's just annoying. But, if it was a long compilation that was going to take 5 minutes to compile, you could say make space ampersand, and it would run your make file in the background. All right, so I can also see jobs that are currently sitting in my system by saying jobs. So jobs shows me a list of jobs that are currently on my system. And so here, when I said jobs, I saw this bracket 1 running looper @. So I could start, a few versions of looper. And now if I say jobs, I see I have 3 jobs running: looper, looper, and looper. And there's this number in brackets in front of them. This is something I can use to refer to one of these jobs. So for example, I could say foreground %3, and that 3rd job is now in my foreground. Now if I hit Control C, it kills that job. And now if I say jobs, I've got 2 jobs running. And if I say foreground %1 and Control C that, now I've only got 1 job running, which was the 2nd looper that I started. And I could say foreground, bring that in the foreground. I can Control Z to pause that. And then I can just say foreground and it'll bring up whichever job has the plus sign in front of it. Or I could say foreground %2, bring that 2nd job in, and then I can Control C that. or so we can say foreground, or we can say foreground percent some number, background percent some number. There's also a kill command. And we can say kill percent number and kill a job that shows up when we say jobs. So let's run our annoying looper jobs again. So I've got 3 loopers running. If I say kill %1, that terminates that first job. And now when I look at jobs, I've got 2 of them running. So I've got both of these jobs stopped right now. And if I want a background one, I could say background %3. And now that job's running in the background. Job 2 is still stopped. I can bring 3 into the foreground and then Control Z it, and now both of those jobs are stopped. And if I want to kill that third job, I could say kill %3. And now that's been terminated, and I have 1 job still paused, which is job 2. I can bring that to the foreground, and then I could kill that with Control C. So we have lots of ways from Bash, from the command line, that we can interact with processes and control them. So Control C kills a process usually immediately. Control Z pauses it or stops it. If a process is jobbed, we can background it, which lets it start running again, but behind the scenes. We can foreground it, which lets it run as if we had just, run the command without hitting Control Z. We can start a job in the background with an ampersand. We can type jobs to see a list of all the jobs that are running or stopped in the foreground or the background. And we can kill jobs by saying kill %, or foreground and background jobs with %. And this is, go and mess with this after class, right? Just make yourself a couple of scripts and play around with running them, putting them in the background, pausing them, killing them, that kind of stuff, right? It's not that complex, but until you actually do it, if it's not something you've done before, it's going to seem kind of weird and confusing. So play with this, right? Get a feel for what these things do. So questions about that?
So correct me if I'm wrong, but I'm assuming the background seems actually really useful as long as your program doesn't print anything.
Correct.
Is that correct?
Yeah.
Okay.
And if you're going to be doing anything at all on your screen, there's really no good way to print. I mean, you could make the screen flash every 5 seconds if you wanted to, hypnotize yourself or something. But yeah, usually we're not going to have output being generated. But there could be something, running in the background that's either performing some task that takes a long time, or, maybe monitoring something, maybe looking to see, if you've been working for an hour, and when it hits that, maybe it, displays a message saying, hey, time to take a break or something like that. But mostly we'll background jobs when we don't really care about, staring at the screen while they do their thing. And this is a case where if we had something that was generating output, we might redirect that output to a file, or maybe to dev null, and just let it run in the background.
Okay, thanks.
Yeah, you're welcome. All right, so let's look at this business of killing a little better. So here's my bash shell. 513.841 is the ID of this bash process. If I were to say kill 513.841, right? So here I'm killing a process, but I'm actually naming the process ID explicitly. So in my bash system, I'm saying, hey, I want to kill this process, which is bash. Oh yeah, put the right number in though. Right, so nothing seems to happen. If I come over here and I try to kill 513841, that bash session dies, which causes the window to disappear. And if I come over here in a new window, I could say kill, and let's kill the process ID of this window, and that window goes away. But the way this is set up, I can't self-terminate, right? I can't kill my own bash session like this. So there's two things going on here to note, right? The first is that it's possible for one process to kill another process that it has nothing to do with, right? I had an entirely separate window, and I was able to kill one window from this other window, different pseudo terminal, different session, and so on and so forth. So that's one thing worth noting. We can have one process kill another process that it didn't necessarily create, that it doesn't, have any particular relationship to. The other thing is that kill does not always do the same thing. In this case, the same kill command is somehow being altered. Bash knows that if it does this, it's going to kill itself, and it's changing the behavior of this to say, hey, don't actually do the kill. And so kill is really an unfortunate name, because kill is not really about killing things. It's really about sending signals. And so a signal is a way to get the attention of a process. And remember, I said most processes sleep, most programs sleep, but they get woken up when certain things happen. Well, a way you can wake up a process is to send it a signal. And if I just say kill, the default signal is term, which means terminate. And that will usually cause the process to end, but not always. So if I say kill -L, I can see a number of signals that I can send. So sig term is signal 15. That's the one that comes when you just say kill. But there's also sig kill process signal number 9, which cannot be blocked. And this will almost always kill a process, even if you're trying not to let yourself be killed. So for example, if I say kill -9 and I put in my own process ID, it tells me, hey, the program bin bash just crashed and I've got a dead terminal now, right? The console program is still here, but the bash program is gone. And so I've broken my terminal. And the only way I'm going to get rid of this now is just to close it out like that. So kill is a general command for sending signals, but the typical signal we send is something like kill or terminate or stop. But it's really a more general facility for passing information from one process to another. And so we usually say kill followed by a process ID, but we can also say dash and put in the number of a signal, and it will send that signal. So kill -9 will kill with a signal 9, and so on. All right, well, this is interesting and useful, because when we write a bash script, we can actually decide how we want it to respond to certain signals. So I can make a function here called, I don't know, I'll just call it haha. This will just be my laugh function. So haha is a function that just prints out ha ha ha, very funny. All right, so I can say let's trap signal 15. And when we get sorry, let's call this haha function if we get a signal 15. All right, so I run this function in the background. So the process ID is 515481. And if I say kill 15, 515481, it says ha ha ha, very funny. So let me change this sleep. So when I run this in the background, it tells me what the process ID is. And so if I send this a kill signal of type 15, the next time it wakes up, it notices, hey, we have a trap set up for signal 15, and it says, oh, let's run this function, haha, which prints out this message. So we can change how processes respond to signals. Now, if we don't trap a signal, it will do some sort of default behavior. So here's a signal called sig_seg_v. That's a segmentation fault. And if I say, let's kill this process with a signal 11, it says segmentation fault. Now, my bash script did not actually get a seg fault, but it received a signal. It happened to come from me. It received a signal 11, which is the signal that indicates, hey, a seg fault has occurred. Now, normally what happens is when your program is running, if you try to access a memory location that you can't access, the memory management system says, hey, that's a problem, and it will send a signal 11 to your process, and your process says segmentation fault, and then it exits. But this is how exceptions are handled in the system. So think about it. You know, if you run a C program and you try to, you know, do a string length on a string that you haven't initialized, so it's pointing to null, you get a seg fault. How does that work? Right? It's not that string length checks to see if your array is pointing to null and prints out seg fault if it is. Your string length function just does what it's supposed to do. It tries to go to a memory location and start looking at bytes, but somewhere there's something, the memory management system, which says, hey, you're asking for data at this address, here you go. And when that system is asked to do something that it cannot do because you don't have permission, it needs to respond to that. And it does that by sending a signal to your process, in this case, a signal 11. And your process responds by saying segmentation fault and then exiting. So sig FPE is signal 8. And if your process gets a signal 8, it says floating point exception. Well, it thinks you just tried to take the square root of a negative, or the tangent of 90 degrees, or calculate 1 divided by 0, or something that is not a legal mathematical operation. And again, the part of the hardware that's responsible for doing mathematics has the ability, if it detects some exceptional situation, to send a signal 8 to your process. And your process says, oh, floating point exception, and then it exits. So signals are also the way that the operating system talks to your processes. and that the different subsystems of the hardware itself, the memory management unit, the floating point unit, and so on, it's the way that those things communicate with your jobs to manage exceptional or unusual conditions. All right, SIGINT is signal 2. And when you do that, your job just dies. SIGINT is the signal that's sent when you press Control C. Oh, I didn't expect that. Weird. All right, so let's just look at this, right? So I'm running my script. It's printing out, every 5 seconds. And yeah, no. And you know that if you hold down Control and press C on your keyboard, that's going to end your script, right? But how does that work? There's nothing in this script that's doing a read statement. There's nothing in here that's monitoring my keyboard to say, has the user pressed down Control and C at the same time, right? This is happening completely in the background. And the part of the operating system that's monitoring my keyboard, if it sees that I've held down Control and pressed C, it will send a signal to this process. But it looks like if it's running in the background, signal 2 is ignored. But let's play with this. So we set up a trap statement to trap signal 15. Let's trap signal 2. And let's run looper. So I'm running this in the foreground. And every 5 seconds, it's going to print out hello. And if I hit Control C, it laughs at me and continues running. And so I've written a program that I can't interrupt now. And sometimes this is useful. So if you're in VI and you accidentally hit Control C, it does not end the VI program, because ending an editor abruptly is usually a bad thing. It's usually an accident. When you're looking at manual pages, if you hit Control C, it doesn't take you out of the manual page command. And so sometimes this is useful to do, but you got to be really careful with this, because most of the time people expect Control C to end whatever it is they're doing. And if you write a script, no matter how cool it is, no matter how great a high-low game it is, if you have a script that Control C does not get you out, people are probably not going to be really happy with it, unless there's a really good reason for that to be the case. So we're trapping this, but we're choosing not to get out of here. So how can I deal with this? Well, I can hit a Control Z to suspend it, and then I could say kill %1, and that'll kill it. Or I could go to another window and I could kill it with a signal 9. And signal 9 is not trappable. So it's one of the few signals that cannot be trapped. They don't tell you that here, but this is the final hope for killing a process. And almost always that will take care of the process. If there's something really weird going on, it may be that a kill 9 doesn't actually kill it. And then you got problems on your system. All right, let's see. She made it say hello instead of printing it, and then download it onto your friend's computer. You have a fast method to end friendships. Definitely. Yeah, so you can get into all kinds of good stuff with this. And I used to inadvertently leave myself little bombs here and there when I was learning this. I'd like make something and I was like, oh, this is really cool. I'd call it Run Me or something. And inevitably somewhere down the road, I'd stumble across it and I'd be like, I wonder what this does. And I'd run it and I'd get stuck, All right. So that's some of how we can do all this stuff from Bash, right? And mostly we care about, you know, running something in the background, moving it between the foreground and the background, pausing it if we want it to go into the background, killing it. That's pretty much it. And trapping signals, pretty exceptional situation. But, you know, there might be something you're doing. For example, in your calendar program, right, you may have a situation where you're reading a copy of the appointment file and building a new appointment file, and maybe you're deleting appointments, right? If during that while loop somebody were to control C your script, your appointment file might not be completely written. You might have only written out the first half of it, and then the person hit control C, and it's possible your appointments have been lost now. So that might be a situation where you would try to trap control C. Or, you know, if this is a Windows utility, it just says, do not turn off or restart your computer while this is happening, right? Well, that's the same idea. It's a critical section of code that needs to complete once it starts. So you can trap, you know, these basic interrupts like a control C, for example, just to prevent somebody from happening to hit that at the wrong time. But usually it's not something we worry about.
So, how does trapping work with like nesting? Because like, for example, our program, our appointment program, if you hit control C, it will take you back a page. But what if we wanted it to just, you know, kick it out? Could you trap it in the very top function, the main program, or would you have to trap it every place?
I think the trap is persistent for the duration of the script. But once you trap it, you have complete flexibility over what you want to do. So the normal behavior is right now, if I get a signal 2, I'm going to execute this function, and then I'm going to continue wherever I was. But, you know, I could do something like this. And now if I hit control C, it says, haha, very funny, but then it exits.
So trap is more like a it listens to a signal rather than it's a listener that you can send that calls a function rather than like an error handler.
Yeah.
Okay.
And there's a way to undo it also, I believe. Yeah, so I can do something like this. So the dash will say, hey, if you get a signal 2, go ahead and do the default behavior. So I think what this is going to do is it's going to trap the first control C, but then it's going to turn off that trap. And then the second control C should respond as usual. So there's my first one, which printed out that message. There's my second one. So you got options as usual. Let's see, using associative arrays with dialogue should not be any different from anything else. I mean, there's nothing special about associative arrays per se. But if you're having trouble using it with dialogue, my suggestion would be if you want to, you know, pull something out of an associative array and use that to create a checklist or something, do the associative array access first, pull the thing out that you want, put it in a variable, and then use that variable in the dialogue command, instead of trying to do it all in one line, because the syntax is fairly complex for, you know, pulling something out of an associative array, and you might get tangled up with single quotes, double quotes, curly brackets, things like that. But just access the array, save what you want in a variable, and then feed that to your dialogue command.
Yeah, I tried doing that and I tested it with an echo statement and it echoes correctly and prints out the information. But for some reason, if I take that new variable and throw it in the dialog statement or just try to do it directly, it just prints out nothing.
Okay. Yeah, so that would be a good office hours discussion, to actually see the code. Keep in mind that spaces are not your friend. So if you're displaying something that has spaces in it, it's kind of a nice hack to get rid of the spaces. So, you know, you can run your strings through a sed line to change all the spaces to underscores, for example. And if I try to add this to a dialogue, I may get into trouble, especially if it's something like a radio list or a checklist, because it's going to see this as 3 separate fields. Whereas if I do this, it's going to see that as 1 field. And it's a bit of a hack, but it's a harmless hack. I mean, this is perfectly readable compared to that previous line. So I don't know if that might be something that's going on also, but spaces always create special conditions in Bash, including with arrays.
Gotcha. I'll give that a go. Thank you.
All right. Awesome. You're welcome. All right. So let's look at how we do some of this stuff from C. And I'm going to need different ones of these libraries depending on what functions we're playing with. So I'm just going to include them all right now. And the first thing we want to look at is this function called system. And system is a function that we can call from C. And it basically executes a shell command. So we can say system, we can give it a string, and it will execute that command. So I'm going to say system quote date. So I'm going to print out the date is, and then I'm going to call system with an argument of date. And at this point, it should create a new process to execute the command date, and the output of that command will just appear on my screen. So if I run this, it tells me the date and then the date is. Well, this came out backwards. Let me fix that first, and I'll tell you why that came out backwards. All right, so the date is Tuesday, 22nd November. So this is a print statement. This is running a bash command. A bit of an odd quirk there. If I didn't put that new line at the end, the stuff came out in the wrong order. So any idea why? Why does the new line change the behavior, change the order? This is a nice interview question. So remember what we've talked about in the past about buffered output? And remember the flush statement, F flush? So because IO is relatively inefficient compared to, you know, I equals I plus 1, which happens in, you know, a few nanoseconds, sending output to the screen takes a long time. And so if the user is going to display a bunch of information, you know, we would not send a T followed by an H followed by an E. This print statement is certainly going to try to print all of this at once. But since there's not a new line at the end, the assumption is the person's probably going to print something else. They're going to have another print statement like, print %s, comma, variable D, right? And so the system buffers your output. It takes the date is, and it doesn't send it to your output display. It saves it in what's called an output buffer. And as you print more things, those get appended to the end of the output buffer. And at some point, that output buffer actually gets sent to your screen. So when does that happen? It happens when you eventually print a new line, or it happens when you do an F flush, or it happens when your program exits. So this output got buffered, but it didn't actually appear. The date command executed, which showed us the date. So we saw the date coming out. And then we hit the end of the program and it said, oh, I've got some buffered output. Let me go ahead and push this out. And so it displayed the date is. So I could have done an F flush on standard out. And then it would say the date is followed by the date command. All right, so that's a little bonus material. I predict at some point, at least one person in this class will be asked that in an interview. So there you go. All right, so that's the system command. So let's do a PS-L and see what that command looks like. And this looks pretty interesting. So here's my bash shell. All right, this is process 106. Bash is the parent of process 226, which is running my program. That's main. So when I type main, a new process is created. That's 226. That's this process right here. 226 created a new process, which is running SH. SH is another shell. It's not the Bourne shell. It's not bash, it's SH. It is the Bourne shell. That's what it's called. And that was process 227, which is the parent of process 228, which was actually executing the PS command. Now, if I do PS right now, I don't see any of that. I just see my bash shell and the PS command. But when I run main, I've got 3 new processes: the main program, shell, and PS. And main created shell, and shell created PS, and PS made this output. And the whole thing was started by main, which was run from bash. So if you look at the system command again, it tells you that system basically runs the shell sh to execute your command. All right, so we can do some basic things with this. Right, I can execute any Unix command I want. So, I can say ls-l, and I can see, all the files in my directory. I can take ls-l and pipe that into word count. And I can see, how many lines of output I have here, and how many words and how many characters. So this system function is really powerful. You can send, pretty much anything that you want into it. I could say remove main. And so now if I run main, it gets rid of itself. Right, and if I try to run it again, it's not there. So I can recompile it and I can run it. But when it runs, it deletes itself. So system's really powerful. You can do a lot of stuff in it. This is part of why I run student submissions in a sandbox, because you could put a system in there that deletes all my files or something. Not that anybody here would, but it's really easy to make malicious C code, right? So you never want to run something that you download without looking at it, unless you really trust the source it's coming from. All right, so that's system, and that's a good sort of first go-to. And sometimes people will just use this to run a command like clear. So clear clears your screen. And so if I say system clear, and then I print something, I get this out at the top of the screen. And some people do that in their programs to give you a clean palette. So that's not a bad function to know about, but it's fairly limited. So if we want to do something more controlled, we can start looking at processes and how processes actually come into being. And the function we're going to talk about here is called fork. And fork's a bit of a dangerous function. You got to be careful when you play with this. If you're going to play with this on your own, I suggest doing it in a virtual environment. Don't do it on your main laptop. Don't do it on the Linux server. But, hop into VirtualBox, make a virtual machine that you don't really care too much about. And you can experiment freely in that virtual environment. And so what does fork do? So fork is used to create a new process. Sorry?
I said it was similar to spoon.
Yeah. Fork is used to create a new process. And it's really a clone operation. Because, what process are you going to create? You're going to create a process that runs ls or runs rogue or what, right? So fork is really a clone. And so let's do the following. Let's say we're ready to call fork. And then we'll call fork. And then we'll say we're done with the call. And then we'll do a ps-l inside system. All right, so check this out. So it said ready to call fork. It printed out done with call twice. And we got 2 copies of our ps command. So let's just look at this first set of output here. So there's our bash session. That's process 106. 106 created a process called main. That's process ID 589. 589 created a new process, 590, which is also called main. And then 589 and 590 each created a process called sh. Those are processes 91 and 92, and 91 and 92 each created a process called ps. So we've just seen a clone operation. In particular, once this call to fork was made, we got a second copy of the process that was already running. And both of those copies were sitting at this point in their version of the program. They both printed out done with call. They both did system. And so this line of output down here came from that second copy of the process executing the ps command. And so there's the bash process, there's the main, there's another version of main, but this one is listed as defunct. And this process main, which was 89, thank you, was the parent of this process, which was shell. And that's the parent of this process, which is ps. But this other shell and ps seem to have disappeared. And this main turned into a defunct process. And if we look at our state information over here, the ps commands were both listed as running. Well, the ps command down here is running, the other one disappeared, but look at the state on this main process that says defunct, it's a Z. So Z means zombie, and this is a zombie process. So what is a zombie? It's something that's been killed, but it's still walking around. And that's exactly what this process is doing. It's been killed because it hit the end of its program. And at that point, the system kills it. But it didn't die completely. It's still here. We can still see it in our PS. So it has a state of Z for zombie. Now, if I do a PS at this point, everything is gone. It's all cleaned up. All right, so here's our process. Here's our call to fork. At that point, we get a new process. And this new process is a clone of the old. What's going to happen if I do this? What if I call fork twice?
Will it do the same thing twice?
Yeah,
Yeah.
so I'm going to call fork. I'm going to get two processes. But remember, each of those is a clone of the original. So now I have two processes, each about to execute this statement. So this will call fork. And this will call fork. And that will cause this situation. And if I call fork a third time, well, now each of these is going to call fork. And we're going to get a clone like that. And we're going to get 8 processes. So let me just call fork 5 times. And let me run this. And take a look at our output here. So this is why forks can be a little dangerous, because you might not expect all of this output to be produced from, you know, a 10-line program. And this hasn't done any harm, but you can probably see the potential for unintended side effects. All right, this is all still the output from that one program. There we go. That's where it starts. So lots of output. And if I do PS right now, you know, everything has exited. But if I call fork inside a while loop, that will theoretically crash the machine. Now, if I do that on my laptop, it'll definitely crash my system. If you do it on the server, it should catch it and stop it from doing damage. But don't try that. Because it will make your friends unhappy, especially if they're in the middle of editing PA5 when the system goes down, because you made a fork bomb, which is what this is called. But, you know, theoretically, it's that simple. Just, you know, while one fork. And each time that you create a clone, that clone and the original will each make a clone. And, you know, in a few milliseconds, your system will either come down or you'll run out of process slots and your process will terminate. And it's fairly easy to do this accidentally without meaning to. All right, so let's go back to a single one. So I'm calling the created process a clone of the original, but that's not 100% correct. So if you've ever tried to clone somebody, you know that you got to remember to somehow make the clone different from the original. So, you know, you put a little dot on their eyelid that you don't normally notice, but if you look, you can see, oh yeah, that's the copy versus the original. right? If you don't do that, if you really make a perfect clone, then the original and the clone both swear that they're the original because they have the same memories, the same experiences, the same physical structure. There's no way to tell one from the other. So fork does the same thing. So the child process is an exact duplicate of the parent, except for the following. The child has a unique process ID. So that's going to be one difference. The child will have a parent process ID, which is the same as the parent's process ID. So that's the inheritance. And there's a few other differences, but the most important one for us is the return value. So after the call to fork, the parent gets the PID of the child, and the child gets a return value of 0. And that's the thing you can use in your program to know if you're the original or the copy. So let's save the value of result in fork. And let's just print out the value of result. So now when I run this, I'm ready to call fork. I got 2 messages saying done with call. One of them said result equals this. The other one said result equals 0. All right, so we can use that to self-identify. So now we can have each process look at the value of result. One of those processes will see that it's a 0, that's the child. The other one will see something non-0, that's the parent. So there we go. So we call the fork, and now you got 2 processes. They can separate themselves out. I haven't seen the prestige yet. All right. So why would we want to do this? Why do we care about this? So the kind of existential answer is, if I do PS-ELF, I can see every process on the system. Most of these processes were created from one initial process. And it's usually a init, right? So this is the first process that gets created. It's process ID 1. And then process ID creates these other processes like cron and kernel processes and system daemons and things like that. And this is what happens, when I say date, well, there needs to be a process created to execute the date command. And so how do we create that process? Well, the first thing bash does is it calls fork to make a clone of itself. And then that clone recognizes that it's the child. And so instead of being a copy of bash, it changes itself into what it has to do to run the date command. And then it exits. So this is why when you run a command, it's got its own process ID, because it's really a separate process. But there's other reasons why we might care about being able to create a process. So for example, you're writing a word processor. And word processor, you type text and it saves it in the file and it formats it and stuff like that. And maybe every 5 minutes, you want to save what the person has typed so far to a file so that if something goes wrong, the computer crashes, their work doesn't get lost. So you want an autosave feature. And maybe the autosave takes 10 seconds to go through and save the file on disk and maybe push it out to the cloud. Well, if I don't have the ability to create a new process, then, you know, somewhere in my code, I'm going to say, okay, you just typed 1,000 new characters. So let's call our save function. And that save function is going to take 10 seconds. And during that time, the person's typing on the keyboard and nothing's coming out. And then 10 seconds, you know, your save function returns and everything they typed suddenly appears on the screen. It's really annoying. If we can make a new process, though, we could just run that in the background. So we detect it's time to save the user's work. We go ahead, we call fork to create a new process. That new process looks at the return from fork, figures out it's the child, and so it goes ahead and does what it has to do to save. And it can take 10 seconds, it can take 30 seconds. It's a separate process. And the main process where the person's typing and seeing their output, that gets to continue running at full speed, and there's no interruption. And there can be lots of situations where we want to run things in the background. And so, you know, making a clone process is a first step to that. All right, other questions on that? All right, so let me talk about one more aspect of processes, and I think we'll be out of time. Let's look at a function called execv. And execv is one of a series of functions that are used to execute a file, which sounds like a useful thing to do, right? So execv takes two arguments. It takes a path name to a file, and then it takes an array of car pointers, which happens to be called argv. And it happens to be called that because it is exactly argv, the thing that we get as an argument to our main program. So let's try this. So I'm going to print a message saying I'm ready to call execv. And then a message done calling execv. And in between, I'm going to execv, and I'll do the date command. So where's date? It's under bin date. And I'm going to have to pass an argv array to it. So I'm going to have to build an argv. And don't get too bogged down on this. I'm just going to make an array of 2 character pointers. So argv bracket 0 is just the name of the program we're running. So I'm just going to call that date. Argv bracket 1 is null because I'm not going to put any arguments on this. And this should execute this program. This is different from system. System is running a Linux command. This is actually executing a file that contains executable code, right? /bin/date is a file of 1s and 0s. It's the executable stuff that makes up the date program. And we're saying I want to execute that code, which means, you know, load it into memory, call its main program, pass this argv array to the main program, count up how many arguments we have till we get to null and set that to argc and call main with those 2 arguments. All right, so if I run this, it says ready to call execv, and then it prints out the date, and then it exits. So what's missing from our explanation here? What did it not do that we might have expected it to do? It didn't print out that it was done calling. This statement never got executed. So here's what exec v does. It doesn't just go off and somehow magically execute this program. It basically changes itself into this program. More specifically, as this program is executing, when it gets to this function call, it will rewrite its own memory. And it'll write its memory with the contents of this file. And then it will adjust its program pointer to the location where this program begins. And once it does that, it is no longer this main program. It's now /bin/date. And so when bin date exits, it returns back to the operating system. And this print statement is nowhere in sight. So these exec functions don't just execute something, they really change the current process into a totally new creature, which is, you know, this executable program. So if you look at exec and you come down to the bottom where it talks about return, if command is specified, exec shall not return to the shell. Oh, I'm on the wrong exec. Exec. So the exec function returns only if an error has occurred. So if something goes wrong, if I don't have enough resources on the system, then this call will fail, and then I would come down and I'd say done calling. But if this call succeeds, I never go beyond it. All right, so let's make this a little more interesting. So if fork returns a 0, I'm going to be the child, and I'm going to execute the PS command. And I'm going to set up my argv array to be PS with this argument of -L and then a null. All right, so I'm going to make a clone. If I am the child process, I'm going to call bin PS. And once that happens, I should never get down here. I should never come out here. I should never do any of the rest of this. So if I come down here, I'm not the child, I'm the parent. I'm just going to go ahead and sleep. All right, so what does this look like? Here's bash process 106, which is the parent of main 254, and 254 is the parent of PS. All right. So if I'm the child, I'm going to do a PS using the system command, and then I'm going to call exec v, and I'm going to do PS again. So my bash shell is 106. That created the main program 262. That created a second main program 263. 263 called system, which created a Bourne shell 264, and that ran PS. And then I called exec v. So there's our bash process 106. It created our main program 262. But look at the process ID on this PS. This is process ID 263, which used to be our main program. So this was the clone of main, process ID 263. But then after we called exec 263, same process is now executing the command PS. So that's what the exec function does. It changes the essence of a process so that instead of running one thing, it's running something different. And it's very different from the call to system where, you know, this was still the program main, but it called SH and SH called PS. In this case, the program main actually changed into the command PS. All right, so that's what an exec does. All right. There's a lot more we can say about this, but like I say, you'll encounter these concepts in future courses at a university. If we have time next week, we can continue down this path and get into some more details, but that's probably a good overview for now. So I'll leave it at that. Finish up PA5. I think people are in good shape on PA5. I'm seeing lots of good dialogues and such. So finish whatever you need to polish on that. Submit it by the deadline Friday. And I will have office hours Tuesday morning, and then I will see people in class Tuesday starting at 10. We'll start doing presentations. Hope everybody has a great rest of the week. Good holiday if you're celebrating, and I will see everybody next time. All right, thank you.
Bye.
Bye.